Welcome. This is a time series analysis course. My name is Nicoleta Serba. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods, and in this lesson, I'll introduce yet another time series modeling approach. This time, this model is applied more generally to multivariate time series. The model presented in this lesson is the simplest formulation of the state space model. More complex state space models can be developed in a similar way as presented in this lesson. The idea behind state space models is that the driving forces behind the evolution of variables or time series are, at least partially, not observable or measurable. For example, one's education level can be driven not only by exogenous factors such as access to schools and income level, but also by many hidden factors such as special abilities which cannot be measured directly. Economic theory suggests that macroeconomic variables such as GDP are driven by unobservable factors, for example, technological change. The VAR model introduced in this course only can account for exogenous variables, which are measurables and observable. The state space model is an extension in that it can also account for hidden factors. Formally, a state space model for an observed multivariate time series of dimensionality W, yt in this slide, depends linearly on an unobserved or hidden multivariate time series xt, also called the state process. Yt is thus the linear transformation of xt plus a white noise process. This equation means that the observed time series process yt is dependent on the state process xt. The hidden process xt takes the form of a var of order 1 if the ft does not depend on t, or more generally a so-called Markov model. We'll learn in the next lesson that the ARMA model is a particular case of this model. In the model formulation from the previous slide, the first equation is called the state or transition equation, and the second equation is called the observation or measurement equation. Some important assumptions are as provided on the slide. Most importantly, the error process Vt and Wt have mean zero, but their covariance matrices can depend on t, hence modeling contemporaneous dependencies. For most of the discussion of the state space model in this lecture, we assume that the data are from a Gaussian process. However, it does not have to be, as we will learn about a more generalized form of the model in the last slide of this lesson. Here's a subset of particular cases of state space models. For example, the AR model and the VAR models are easily derived as state space models since the hidden process xt model is defined as the AR-VAR model. In fact, many econometric models, in particular time series models, can be written in state space form. This obvious flexibility of the state space model approach has contributed much to its popularity in recent years. We can define a similar property of stability for a state space model as for the VAR model. If we consider the special case in which the covariance matrices of the error terms Wt and Vt do not depend on time, then we have stability if all eigenvalues of f lie strictly inside the unit circle. This property is very similar to that of stability of a VAR model. We can also guarantee a unique solution to the system of equations under the stability condition. Here we see the direct connection between the state space model and the ARMA model. If yt is a stationary ARMA model, we can write yt as a state space model where yt is a linear transformation of the hidden process xt, and xt is a var of order 1 model with the matrices f and g provided in this slide. The F matrix in the VAR model for xt is merging an identity matrix with the last row, including the AR coefficients. The G matrix is the linear transformation of xt and is simply the vector of the MA coefficients. Last, the error term process includes zeros except for the last term, which is specified by zt plus 1, the error term of the ARMA process at time t plus 1. The state space model introduced in the previous slide is the simplest representation of a state space model. We can generalize this model by modeling the conditional distribution of the observed time series yt given the hidden time series xt with a more general distribution which represents the observation distribution. Similarly, we can describe the one-lag dependence of the hidden process xt or the conditional distribution of xt plus 1 given xt with a more general distribution, which represents the one-step transition density of the Markov process. This model applies to more general distributions, for example, time series of Poisson counts or intermittent spikes. This generalization is in the same realm of generalized modeling when extending the multiple regression model to generalized linear models. The distribution of the data or of the error terms does not need to be normal. It can take other distributions such as the Poisson distribution. In summary, in this lesson, I introduced the model, the state space model, which applies generally to multivariate time series. Thank you.